compact object at the center of our galaxy. This year, we have the honor of having 2 Nobel Prize laureates here to give a talk. Due to time constraints, it won't be possible to ask questions at the end, but I hope, or we hope, that the fact that we have 2, well, makes up for this. First, we start with Reinhard a German astrophysicist, co-director of the Max Planck Institute for Extraterrestrial Physics, a professor at LMU, and an emeritus professor at the University of California, Berkeley. And ReinhardGenzel studies infrared and sub-millimeter astronomy, and he and his group are active in developing ground and space-based instruments for astronomy, and they use these to track the motions of stars at the center of the Milky Way around Sagittarius, a star, and show that they are orbiting a very massive object, now known to be a black hole. Genzel is also active in the studies of the formations and evolution of galaxies. It is my privilege to give the digital floor to ReinhardGenzel.
Diederik, thank you very much. Now let me see. Let me try to share with you my slides. Okay, I hope you can see all of this. So what I will do is to describe to you a lengthy journey, actually, for me personally, but also for the scientific community in testing general relativity in a limit which really was not possible until a few years ago, and in fact experimentally show that one of the early predictions, namely the existence of black holes, of these bizarre objects, actually is a reality. Now, let's all reflect that GR is 105 years old. So it's a remarkable thing that after 105 years, the number of publications in this field is growing exponentially. And only recently, actually, has there been experimental evidence of the type which you would, as physicists, accept. So, of course, there's the fantastic theoretical work, starting with Einstein himself, the first solution by Karl Schwarzschild, showing the concept of the event horizon, also the singularity. I leave this theoretical part to Roger Penrose, who's speaking later. So I'm the experimentalist who, of course, wonders whether the predictions of the theory that there are these objects where light cannot escape, and perhaps there are singularities at their centers, actually have been realized in nature. And as you may know, it took a long time, 50 years. In fact, about the time when Roger and Roy Kerr and others started working on new aspects of the theory, when in fact the first evidence came in form of compact X-ray emitting binaries on the one hand, and objects we call now quasars on the other. The binaries we think are stellar black holes, and we'll come back to this in a minute or so. The quasars were postulated after some theoretical work to be accreting black holes, thereby using the fact that while light cannot escape from within the event horizon, you can release enormous amount of energy of gas and also stars, which are falling into the black hole and just outside of the event horizon. So for a maximum Kerr hole, about 40% of MC squared can be released, and thereby you might be able to understand these spectacular objects. That was the birth of the concept, the paradigm of massive black holes in the centers of Milky Ways. But how would you test that? How would you test that from a physics perspective? Well, you would have to go in there and send a rocket in there and measure gravity, of course. That's what we do, right? But these objects are far away. The first one, which was discovered several billions of years, and we have now objects which are basically all the way almost to the Big Bang. And so they are much too far away to do any detailed dynamical tests of gravity. But Lindenbell and Rees in 1971 proposed that, well, if the quasars are just sort of special objects, special galaxies where massive black holes reside, but are accreted, maybe other galaxies, including our own, might have such black holes, only not very much accreting. And in fact, that paradigm then led to an increasing amount of activity observationally, and that included then also myself, as I will describe, and led, in the case of the Galactic Center work, by our group working with the European Southern Observatory and Andreas Gesse's group working with the Keck telescopes, to a really rather impressive set of observations over 40 years. In my case, it's been 40 years, to make a case which is now fairly sound beyond any reasonable doubt. At the same time, the objects which I mentioned as X-ray emitting binaries sometimes spiral together and emit gravitational waves. And that too has now been all of a sudden possible to measure and led to another Nobel Prize 4 years ago, 3.5 years ago, and is now a new field in astronomy. Finally, while the gravitational waves and our infrared waves are probing some aspects, the radio astronomers with intercontinental interferometry can look at the emission of short wavelengths, microwave emission at very high angular resolution, and thereby, if you like, make an image. The first such image was published 2 years ago and led to a beautiful result of as expected from GR, from a light emitting ring around a darkish region, which is interpreted to be basically the photon ring around the black hole. So that's 100 years. In the Galactic Center, this work allows us to go in particular detail because the Galactic Center is only 27,000 light years away. The problem is that you cannot work there in the optical, because between us and the Galactic Center is an enormous amount of interstellar dust, which extincts the visible radiation. But if you go to infrared waves, 4 to 10 times longer, or radio waves or X-rays, then you can look into the center. And when you do that in blue here, on a scale of a few light years, you see a very strong concentration of stars, very bright stars, remarkably so, actually. And in the middle of that region is a compact radio source, Sagittarius A star, which with radio interferometry we now know is at 1 millimeter smaller than about 40 microarcseconds. That's remarkable, 40 microarcseconds. That's about a few times the size of a euro cent coin on the moon in angle. Now it turns out that this radio source in this star cluster is also embedded in a set of streamers of gas. The pink stuff is ionized gas, and the green stuff is neutral gas. And these gas clouds move, and you can measure their Doppler motions. And in fact, that was the first experimental evidence that there might be a central mass concentration, a black hole of a few million solar masses. Charlie Towns, Nobel laureate for the invention of the meson laser in later years, went to Berkeley and moved to Berkeley and started doing astronomy. And he and his students and postdocs, and I was then one of them, used infrared equipment, infrared spectroscopy, to measure the motions of these ionized and neutral gas clouds. And they moved obviously so fast that it required a mass of a few million solar masses in the center of a few light years. Now, you don't know whether that must be a black hole. It could be one. How would you find out about it? Well, you have to remember Kepler's laws, right? If there is a point mass in the center of a region, like in the solar system, then the motions of test particles around it depend with 1/square root of the radius. So if you go further out, the motions are slower. And indeed, in the innermost region, we could show that to be true, but then you go outside of a few light years and the mass, the implied mass, increases again, which is basically the stars. So this was the first evidence. Now, is that a black hole? Well, a few million solar masses is a pretty impressive number, but at about a light year or so, you're still a million Schwarzschild radii away from what would be a black hole. So you cannot be sure. And so the work of both groups who then started working on this involved over these many years lots of continuous improvement on new technologies. For instance, low noise infrared imaging detectors, which at the time when we started in the 1980s was not available. Then the technique of adaptive optics, where if you observe on the ground a distant star or at the galactic center, then the Earth atmosphere, of course, distorts the wavefronts. Now you could, of course, bring a telescope out in space, like the Space Telescope, but that's too small for our work. Instead, we are analyzing the wavefronts by looking at a bright star in the field and then using a deformable mirror inside of our equipment to straighten the wavefronts out and thereby correcting the distortions with what we now call adaptive optics. All modern telescopes are now equipped with adaptive optics. Sometimes actually there's no bright star, and so then you actually have to bring your star, make your star, by shooting laser light into the upper atmosphere, focus it there, and use resonant backscattering by sodium atoms up there to generate an artificial star. In summary, I mean, I just want to give you the feeling that, you know, it took 40 years to come to a sort of not a final result, but anyhow, a very strong result, because we had to continuously improve the technology, get better detectors, bigger telescopes, adaptive optics, and as you will see, we even now are using the combination of telescopes to interferometry. Then you have to wait and see whether you can measure the motions of the stars, for instance, on the sky. And here, this is a little movie. And so you observe over years to see these motions. It's actually remarkable. In astronomy, usually you cannot see motions directly because typically things are too far away. Not so here in the galactic center. And so you see these motions, and when you analyze these motions, then actually you see that they're parts of orbits. In fact, in one case, one star, we are lucky. Nature has given us a star which is on a highly elliptical orbit within a period of about 16 years, which penetrates at its closest to the radio source Sergei star to about 3 times the orbital radius of Neptune. It moves there with about 2.6% the speed of light, 7,600 kilometers per second. So if you take Newton's laws and calculate what v squared over r over g is, well, we'll find it's a few million solar masses. So the same mass we had seen earlier, 10 years earlier with the gas, but now much, much closer in. So this Perry approach is about 1,000 Schwarzschild radii. But must it be a black hole? Well, it's pretty plausibly a black hole, but we really need to get closer in, and our analysis of that this might be a black hole very much relies on the assumption that general relativity holds in this regime. Of course, we knew the first Perry was in 2002. We knew that the star would come back in 2018, and so our group then worked with ESO to develop a combination of all the 4 8-meter telescopes on Parnell Mountain. You see them there, and bring the light together from each of the telescopes in an underground tunnel system, correcting the wavefronts, etc., etc. I don't have time to get into the experimental details, to build a machine which then can effectively have the resolution of a 130-meter diameter telescope. So that is milli-arc-second resolution, and we can measure with a precision of 10 to 50 micro-arc-seconds. So right at the scale of the event horizon and a little above. So that allows us then, with this machine, which we call Gravity, built by a fantastic team headed by Frank Eisenhower, a European team. That allowed us then, when the star came back in 2018, to measure its motion from night to night during the Perry approach. You see the green points are the positions of the star. The black hole is the black circle. And the closest approach happened in May 2018. And I mentioned already the motion there is about 2.6% the speed of light. So what did we see? Well, we saw indeed a number of the effects of general relativity. For once, the so-called gravitational redshift, which is basically the clocks are going slower in strong gravity fields. So if you plot the Doppler motion residuals of the motion of the star, then because of that shift.
Oh, Mr. Genzel, your microphone is on mute.
Okay, I don't know how that happened.
Thank you so much.
It's all right. That's bad. So you see then, if you compare the motion on the left side there of the star in these red dots relative to the Newton orbit, which is the gray line at 0, you see very clearly the deviations, exactly how general relativity predicts, which is what the blue line is. So this is a very significant detection of the gravitational redshift. Another effect which theory of Einstein predicts, of course, is that the star orbiting a point mass or a compact mass does not move on a closed ellipse, but on a prograde precessing ellipse. Now, for such a highly elliptical precession, that precession is more like a kink in the orbit. And in fact, down below, you see on the left side, the residuals again between the Newton orbit, which is the vertical, the horizontal dashed line, and the observed motion, and red is what general relativity predicts with the Schwarzschild precession. So clearly we have seen the Schwarzschild precession, which in this case on the sky is an angle of 12 arc minutes. So that's much more than the famous experiment which was done to show the precession of Mercury and gave Einstein the great first success and an experimental confirmation. The last thing we've seen is, in fact, motion of gas, very hot gas, very close in at about 5 to 10 times the gravitational radii, where the gas clouds move with 30% of the speed of light. And indeed, that's about what the coordinate speed should be if general relativity holds. So we have very good evidence that this object really is a black hole. Now, of course, let me ask, must it be one? Okay, must it be one? Why has the Nobel Committee said for the detection of a supermassive object and not about supermassive black hole? And the answer, of course, is we are not done yet. We need to go further, measure the spin of the black hole, and show that the no-hair theorem is correct. So that's sort of our business plan for the next years. In the meantime, the situation is such that we've proven where we knew 40 years ago that there was a few million solar mass object within about 10 to the 6 Schwarzschild radii. Now we know that the same mass is there within about 10 Schwarzschild radii. We know that any extended mass inside the orbit of S2 is less than a few thousand solar masses. So there are likely some stellar black holes and stars there, which we're trying to see in order to measure the spin. And any partner of the big black hole, for instance, people speculate that there might be either a binary or an intermediate mass black hole, would have to be less than about 1,000 solar masses. So we can use these measurements now to actually test in detail the astrophysics of a star cluster in such an extreme environment also. So there is the astrophysical part of this work, as well as the physics, which I mentioned to you. Okay, so I guess I'm out of time. So this has been a long but extremely rewarding journey. You might imagine that many people had to work on this over these 40 years, and I'm very grateful to a large team of young and not so young people who've been doing this. And I'm also grateful to the international European collaboration, which really made this all possible at ESO. Thank you very much.
Thank you. Thank you so much, Professor Genzel. We will, of course, send you a small token of our gratitude, or especially engraved glass. But thank you so much for showing us your amazing work and that of your team, and finding this supermassive object and making it plausible, at least, that it's a black hole, and measuring the effects on general relativity in the orbit and the motion of gas. And it's really amazing work. And I hope you won't find any hairs then the next couple of years, and good luck with all the astrophysical measurements that need to be done. Thank you so much for being here.
Thank you.
And well, we've heard from one Nobel Prize laureate about black holes, and now we will hear from another. Sir Roger Penrose is a mathematical physicist, mathematician, philosopher of science, and, well, Nobel laureate. And he is Emeritus Rouse Ball Professor of Mathematics at the University of Oxford, an Emeritus Fellow at Wadham College, Oxford, and an Honorary Fellow of St. John's College, Cambridge, and University College London. He made contribution to the mathematical physics of general relativity and cosmology. He has received many prizes and awards, including the 1988 Wolf Prize in Physics, which he shared with Stephen Hawking for the Penrose-Hawking singularity theorems. And there are many contributions in different fields that he made, and we're honored to have him here. So if you are already here, Professor Penrose, I would like to give the floor to you.
Can you hear me?
Yes, loud and clear.
Can you see me?
As seen as well.
Good, thank you. I hope that's clear enough. And I hope to get my PowerPoint pictures on as well. How does that work? I've done share screen, and then I'm sort of baffled because I see all sorts of things. Where would it be?
In this list, there should be one with the PowerPoint logo.
No, I can't see these things, unfortunately. Where would that be? It's not that one, I guess. Let's see it. I've got my PowerPoint. Oh, here, that's probably it. Can you see anything?
Not yet. If you press share on the down right corner.
Done share. Oh, down right corner, sorry.
Yes.
Share, yes, okay. So as long as I get the right one of those pictures, and I can't see any of them, but let's hope this is correct. No, that's not correct. Oh. How do I get my PowerPoint up there?
Slightly to the right.
Just a minute. I've lost the picture, sorry. I'm an incompetent when it comes to these things. Unfortunately, you have to bear with me.
Well, if you calculate black holes, then other people are better at information.
Well, I can see my picture, but you can't, I guess. No, how do we do?
We can see the picture if you put it on full screen.
Oh. Good. So can you, this is, the main picture there is the picture in my paper, which apparently got me eventually a Nobel Prize. Can you see that picture?
Yes, but if you could maybe put it on presentation mode, then it's more full screen.
Yes, I realize this is something I've not learned how to do. Where would I find that on the screen?
I think in
Slideshow on the top.
The top corner, yes, the top
The
slide.
third from right. View, review, slideshow.
Third from right at the top. Share screen.
Now inside the PowerPoint, underneath the red bar of PowerPoint,
Red bar of PowerPoint. Okay. Yes.
there it says slideshow on the slightly above and to the left, to left, to left, to left.
On the
Left.
left.
More left.
More left.
More left. More left.
More
More
left.
left.
Stop.
There.
Slideshow.
Slideshow.
Slideshow. Okay. Do you see it properly?
And almost slightly down and
Slightly down. What the pinky? The
Function key 5 is worth a try.
sorry.
Function key 5 starts the slideshow.
Key 5. Oh dear. Now how do I find that? See, I have an additional. Apart from being incompetent, I have bad eyesight.
function key 5.
No F.
F5, yes.
F5. F5. I just pressed it. What does that do? Does that do something?
No, it didn't work. So we go back to slideshow. And from slideshow, you get a new list of options and you have to take the up
Where is slideshow? At the top.
to the left.
Otherwise, Mr. Penrose, we can see it. It's slightly smaller. We can see your desktop if that's all right for you as well. Then we are more than interested just to hear what
Why don't I do it like this? Because I shall spend too much time trying to explain.
this works wonderfully.
Let's
So
do it like this. Okay, well, here we have the picture which appeared in the paper, which eventually seemed to have got me a Nobel Prize. This represents a gravitational collapse in the spherical symmetrical case, but I want to show that if you perturb it, you still get a singularity in the middle. And this ring that you see in the middle, you have to imagine there's another dimension. So what looks like a ring is really a sphere. And the point about it is that if you have a flash of light on that sphere, then the light from it is converging. The inward and the outward light flash would be both converging. And this is an unusual thing to have something which is compact and has this converging property. And this was the criterion that I used. It's called a trapped surface. And once you get that, then you can prove a theorem which shows that something goes wrong. Basically, that you get a singularity. In fact, you start off from a surface which is non-compact, which is your initial data surface. And then you get the future of this trapped surface you can show has to be compact. And this leads you to a contradiction. I won't go into the details of that. That's not appropriate here. But I do want to explain the important thing about these pictures is the light cone. And of course, here we have the four-dimensional space-time, 3 space axis and 1 time axis. And the light ray is what you have to gauge things so that if time is in seconds, then the distances are in light seconds, so that the light ray is more or less at 45 degrees. But that's just to get it so that it looks reasonable. Okay, let's go back to the general collapse picture. And here we have the horizon and the singularity, which is likely to be much more complicated, that in the middle. Now, when I had this theorem, I gave a talk in Cambridge. I gave one in London first and then one in Cambridge, and Stephen was present at the second one. And Dennis Sharma arranged that we got to speak together, and I explained the techniques that I was using to Stephen and to George Ellis, I believe, at the same time. And then Stephen picked up on them very quickly and started to apply these ideas to cosmology. So the idea was, well, first of all, before getting into that, let's suppose we have a collapsing universe. You see, suppose we have a universe which time is going up in my pictures normally, and instead of having a nice simple singularity, which you might expect to see when you have lots and lots of black holes and they all start to congeal with each other, you'll get one great mess in the end. And it's characterized by the fact that the Weyl curvature, that's the conformal part of the space-time curvature, and that blows up and becomes horrendously infinite. Anyway, so that's the picture we get for a general collapse. But what about for the situation, more or less what we see in our universe? We see an expansion. Well, we also have this exponential expansion, which plays an important role in what I want to say shortly. But the general picture, of course, the universe might be closed or it might be open. That doesn't play any role in what I want to say. So I've indicated at the back that it might go on forever or it might close up. I don't care for the point of view of this talk. But we do have this Big Bang, which is a singular state. People try to introduce this notion of inflation, which doesn't make any difference to the discussion I want to make. The problem is that why do we not get a situation like this, which is the time reverse of the sort of thing we saw before? A generic singularity would be have these enormously diverging Weyl curvature and very complicated situation. So the real problem, which I began to worry about, is why is the universe like this and not like this? Why don't we have a very complicated initial state? And the argument I was putting forward, if you can put inflation into it as well, it doesn't make any difference because you put your inflaton fields in or whatever you like, and it makes no difference, no essential difference to the collapse being this great mess. And you can see that working out using the Bekenstein-Hawking formula for the entropy, you can see how improbable a situation like this, and it's something like 10 to the power 124, figures like that. So it's ridiculously improbable that the universe was like this. I want to stress this point in a different way. I'm imagining now, this is the top three pictures indicate a gas in a box. And I imagine that this gas is initially in one corner, you open up the box and the gas spreads out throughout the box. So time going from left to right, entropy going from left to right. Entropy is increasing in this situation. Now the bottom two pictures, I'm imagining a galactic scale box with lots of stars in it. And then time still going from left to right, and the entropy definitely going from left to right. You get clumping and you get finally things like black holes. So the entropy shoots up by an enormous factor when you get black holes. So what we find in our universe, this is what's rather remarkable. It's not just that we have low entropy in the early universe, but we have low entropy specifically in gravity because we see uniformity, and this uniformity is consistent with the gas being uniform or whatever. In fact, we see by looking at the cosmic microwave background, there's this beautiful Planck curve for the temperature spectrum, which tells us that it is, as far as the matter and the radiation is concerned, something at a maximum, essentially maximum entropy, whereas gravity is essentially minimum entropy. So we have to explain why it is that gravity is so special, or what it is that well, what I want to do is to move to a different way of looking at space-time. And this, well, it's mainly saying that what's important in the structure is the light cones, and that's all. The null cone at each point is the structure, and this is the conformal structure of space-time. Now, it's very useful to think of conformal structure, and we see this illustrated in this beautiful picture by the Dutch artist M.C. Escher, where you have infinity represented. This happens to be a picture of the hyperbolic space. This is the Beltrami or Beltrami-Poincaré disk. And we have the Escher picture of these fish creatures. One thing I would point out is they have eyes which are exact circles, and they remain exact circles right up to the edge, which is illustrating the conformal nature of this picture, that when they get squashed down, they get squashed down equally in all directions. And so small shapes are preserved, and in particular, small circles are preserved. And this means that you have a conformal picture. But in this picture, that you can represent infinity, which is what I want to use this diagram for, just to show you that with a conformal description, you can represent infinity as in this case, which is a perfectly smooth boundary, and you could imagine extending to something outside the boundary. There would be no contradiction with the conformal structure by doing that. Okay, as I said before, it means the light cones. Now, I want to talk about the whole universe now. And it's a feature of having a cosmological constant, which seems to be the case from the observations made in the turn of the century, basically, and that also a Nobel Prize for the three main people concerned with this. And what they find is something like, well, people call it dark energy. I don't like the term because it's neither dark nor energy. It's transparent. And it's certainly not like energy because it's repulsive rather than attractive. So it's something quite different. It's the cosmological constant or something very much like a cosmological constant. But the feature of this is that the future infinity is space-like. So it's like a time, it's time infinity, if you like. But as far as the causal or the conformal structure is concerned, it's a space-like structure. So we can squash it down, and this is what I've done in this picture, to be space-like. Now, what about the other end? Now, you can, in the models of cosmology that we see with the Big Bang, they pretty well have the feature that you can stretch them out also to make a smooth boundary. But it's quite different because in general, the future, well, if it were a collapsing situation, you would expect to get diverging Weyl curvature and something completely wild. But what we get is something very different. And well, people used to say, well, how do you deal with the singularities? What you have to do is to bring quantum mechanics in, and there's a theory of quantum gravity. And I used to think this too, like everybody else. But then I began to wonder, it must be a very peculiar theory, because if it has the effect of dealing with the singularities in the future, why does it give you a completely different answer for the singularity in the past? Something very, very smooth, something for which the Weyl curvature seems to vanish as opposed to diverging wildly to infinity. It's almost the opposite. So what kind of a quantum gravity could give you that? My answer to this is it's not quantum gravity. It's something where you have to look at it from a conformal perspective. And in the smoothed out models, you can stretch it out and make a nice boundary like this. But what about in general? Well, this was really my student, Paul Todd, who suggested that this would be, and he didn't just suggest it, he worked at it and worked out equations and so forth to what happens in a general case where you have a smooth boundary, which could continue to something beyond, but this is just a hypothesis. You don't say it should continue to anything behind it. You just say that the condition is that it would be smooth enough so there would be a conformal extension if you wanted to have one. But the idea going beyond that is to take it seriously as physics. Now, this is the next step. So what I want to say is it's not just a neat trick, but it's something which is serious physics. More than that, it's something, now this is what's outrageous. Up to this point, I've not said anything which is outrageous, unless you think not believing in inflation is outrageous. But I think inflation doesn't answer the question. You have to have something else. And what I'm saying is that Paul Todd's idea of making it smooth is part of the story. The rest of the story is to say that the Big Bang was the continuation of a previous eon, as I'm calling it. These each steps here are what I call eons. Our eon started with the Big Bang. It's finished in a certain sense as infinity, but in the conformal sense, it finished at this conformal boundary. Now, how can I get away with joining them together? Well, you see, when you have a very cold and rarefied situation, when you squash it down, it becomes hotter. What about a very hot and dense situation? When you stretch it out conformally, it becomes colder. And it's sort of not unreasonable that it should match. Now, it's only reasonable physically it should match if you have the case that the physics is basically free of matter. So you can imagine it has to be zero mass fields. Well, in the remote future, it's dominated, the particles are mainly photons, but it's not quite the whole answer because you do have some other particles, you have hydrogen and things like that. And so I have a hypothesis, which is that the mass fades out in the remote future. One can justify this on certain grounds, which I don't want to go into here. But that's a hypothesis that the mass does fade out in the remote future. What about the Big Bang? Well, there it's easier, because in the Big Bang, things are so energetic that the mass becomes completely irrelevant. The energy in particles is almost completely dominated by their motion and not by their rest mass. And so in effect, the closer you get to the Big Bang, the more and more massless particles are. And so the argument is that in the limit, as you go into the past, things become massless. Into the future, they become massless. And therefore, the physics is the physics of massless particles, and conformal geometry makes a lot of sense in that case. Okay, what about observations? Because this is all right for a hypothesis. I used to think, well, nobody will ever prove me wrong, and so therefore I can talk about this forever. But then I started to think, well, things can get across. So let's indicate this. Photons can certainly get across in principle. If they are long enough wavelength, they could actually get through. And I want to say a bit more about that in a moment. I don't know how much time I have left. It's probably negative, but I hope I can still say a few things. I did wonder about observational tests, and here I have one of them. You must imagine that, well, we had a nice description of a black hole in the center of our galaxy, very impressive indeed. And there is also a black hole in the Andromeda galaxy, a much bigger one apparently. And eventually, not too long, I suppose in the future, in the scale of things, we will collide with the Andromeda galaxy, and eventually our black holes will feel each other out and spiral into each other. And when they collide into each other, we more or less get swallowed by the Andromeda one, which is much bigger, but there will be gravitational radiation coming out from this. Now, in a galactic cluster, there will be many black holes in the different galaxies, and as they come together, they will get bigger and bigger black holes, and you will have eventually several of these collisions, which will send signals out. So in this picture, I'm showing you, this is a cartoon of the crossover, the surface in the middle, the sort of rectangular thing there, is representing the three-dimensional surface, which is the crossover surface from the previous eon to our eon. This is us at the top looking back, our past lifetime, and these are several explosions as the black holes encounter each other, and the explosions in the form of gravitational waves, which will come up and in a sense come through, and the signals will be registered on our microwave background. They will be very faint. I've deliberately drawn them at the bottom as these sort of rings, which we'll see, but deliberately faintly because they're very faint. But they are there, the claim is, and you will see them with having lower variance in the temperature than most other places. So my Armenian colleague Vahi Gurzajan looked for triples of rings which had unusually low variance, but you had to have three concentric ones to get a significant signal. And what did he find? Well, in the Planck data, what he found was the following. This is the centers of these triples of rings. And what's remarkable about it, as far as I'm concerned, is the clumping you see. You see them in three or just rather small number of pretty big regions, but not spreading over the whole sky. What's more remarkable, I should point out that the central three regions here are excluded, so that they stop off there merely because you don't look there. But the centers of these rings are also clumped in color as opposed to just their angular distribution. Color means, well, just means temperature, and red means high, it means higher temperature. It really means blue shifted. So you might think they're more distant, but when you look at the details of the theory, it really means that they're distant. So the red ones are the distant ones according to the theory. And the fact that they're clumped in color means that they are also clumped in their distance from us, not just in the angular distance. So I find this very, very striking that you do have this clumpiness. And if you have another theory which explains these features, I'd like to see it. But it's certainly explained by the cosmological model I'm putting forward, CCC, because, well, it's explained if you believe that there are large regions which are not necessarily super duper clustered, I would say. Okay, that's one piece of observation. Another one is the result of black holes in the remote future. Hawking evaporation will eventually make them disappear, and there will be, all the mass will be concentrated in the radiation, apart from what happens to the eventual singularity here. But this, as you do the conformal squashing, since this happens so late in the universe's history, something like 10 to the 100 years for the very biggest ones, they will be squashed into a single point on the crossover surface. So here I have a picture from a paper written by myself and Christoph Meisner, Daniel Ahn, and Pavel Mirovsky. And it was the analysis done according to a screen by Christoph Meisner, and the detailed analysis was looked at by Daniel Ann. And what they find is, according to this analysis, there are points. Let me see what you would expect to see on the theory. This bottom horizontal line is the crossover from one eon to the next. So this is the previous eon, and above that line is us. The Hawking point, I'm calling it, that is all the radiation and everything that might be left of the black hole is concentrated, because it happens so late, into a tiny little point. So on the other side, it would be a tiny point which is even smaller than the Planck scale. So very, very tiny. But you don't see that because the radiation from it just scatters, and certainly from the work of Jim Peebles and other people, you have a good feeling for what happens here. And 380,000 years, it scatters around and you don't see anything until decoupling and things like this happen, and eventually you can see the radiation coming out. So the Hawking point will then spread out to this region, which is about 4 degrees in the sky, which is about 8 times the diameter of the full moon. So these spots will be, roughly speaking, because all the scattering, be something like a Gaussian distribution, and they will be heated in the middle and cooler as you get to the edge. Maybe for the strongest one, something like a factor of 30 bigger than the normal variations in temperature. You might ask why these things have never been seen before. I think the answer is that just nobody has looked, because they believe, because of inflation and all that, that somehow the cosmic microwave background should be not producing signals like this. But according to the analysis, the significance of the presence of these signals is 99.98% confidence level. Not only that, but the 6 strongest points, well, I should say the 5 strongest ones in the Planck data are also seen in exactly the same places in the WMAP data. You look in the WMAP data and you find another very strong point, and that's also seen at the same place in the Planck data. So those 6 points I consider to be pretty genuine candidates for Hawking points, and they would be if, well, I mean, the theory predicts them, and I don't know of any other theory that predicts them. I would like to see these things analyzed further to see how strong the case really is. Certainly the 99.98% confidence level strike me as something that means you should take them very seriously. Thank you very much.
Thank you so much, Professor Penrose, for your great presentation on the space-time singularities, black holes, cosmology, the fading mass in the future, and the Big Bang. Thank you for taking us from eon to eon and your cosmological model. And we send you, of course, our inscribed glass, and I'm sure that I speak on behalf of everyone. Our sincerest thanks for your presentation.
Thank you.
Thank you so much. Then I would like to continue. It's normally a tradition at Fysica that we visit different universities each year, and that is always interesting to see other places and how they do things. This year, due to Corona, it's not possible, but Professor Steven Hoekstra has a solution. He works at the Rijksuniversiteit Groningen, and he will give us a virtual lab tour so we can visit Groningen during these trying times. Steven, I hope you are with us.
Yes, I am. Let me switch on my devices and share the screen with you. One moment. There we go. I hope you see the first slide, Diederik.
Yes.
That's working. All right, very good. Yeah, so I'm honored to give you a kind of view into our kitchen to look a little bit at what the experiments are looking. I normally always really like to go on a lab tour because you meet the people that actually do the work, right? That are hands-on their experiments, and that's also what we'd like to show you today. So I represent a research program that we do with a whole team, both in Groningen, like was mentioned, but also at the Vrije Universiteit Amsterdam. And actually our whole project is part of NICEF, the particle physics organization in the Netherlands. So before diving into the lab, I need to give you a short introduction to what it is that we're doing actually. So I need to tell you about the electron EDM. It's the electric dipole moment of the electron that I'm talking about. And the question is, can we measure this electric dipole moment of the electron? And so on the picture you see on this slide, you see this fundamental particle, the electron, that in principle does not have much substructure, could actually get an electric dipole moment through interactions with standard model particles, but even beyond the standard model particles. And the magnitude of this electric dipole moment that it would acquire depends on the structure and all the particles that are out there. For that reason, measuring this property of the electron is a good way to test the standard model of particle physics. However, we don't do experiments on bare electrons. We actually use a trick, and that is to have a molecule. Like here, you see a polar molecule, just two atoms together. The atoms are not the same. And inside this molecule, you get a hugely amplified electric field. And this large electric field, we can use to explore the properties of the electron. So the key thing is, by measuring something on a molecule, you can learn about the electron. And this enhancement is about a factor million. It's really gigantic. So with this idea in mind, we started a program for a number of years now to exploit these properties of molecules and actually make a molecular beam, a very intense molecular beam, in our case of barium fluoride molecules, where they fly from the left to the right. Well, I don't really want to talk too much about the details here. There's also no time for that, and I would like to actually give the stage to the students that actually do all of the work here. I would just like to show that this idea of making this experiment, we of course need to translate into a machine. We call this tabletop particle physics. It's about a 8-meter long table, so plenty of people can join. And we also need a kind of a good team of people with expertise from particle physics to molecular physics to optical physics and magnetic shielding. So I would like to introduce mainly this team of people. These are the PhD students that are working on our project in recent years, and they will take you to the lab and tell you and show you what they're doing in the movie that I hope will run now without any technical issues. So here we go.
Hello everyone, my name is Maarten Mooi and I'm working here at the VU in Amsterdam on optimizing the molecular source for the electron EDM project, which we do together with the University of Groningen and PKF. I'll show the key elements and hopefully you get some idea of how my life in the lab looks. So first of all, we work with vacuum, so we have vacuum chambers here, and you're lucky as we opened the vacuum here and pulled out this top part, so we can reach the parts which are normally inside the vacuum. We can easily reach now and upgrade. Now, we make barium fluoride molecules by a reaction with a barium target, where from this target we ablate barium atoms by an ablation laser. Hopefully my camera can record it. As it's a few nanosecond pulses, my camera sometimes has difficulty with it. And we let those atoms ablated from the target react with SF6 gas and to form barium fluoride molecules. These molecules are hot and fly in all directions due to the ablation and the reaction. But we do this inside the cell, and this cell is 20 Kelvin, and through this cell continuous neon atoms flow, and therefore the barium fluoride molecules will collide with the neon atoms and thermalize to the 20 Kelvin of the neon gas, and will be extracted in this neon gas outside the cell. It's good to make the beam. We want to optimize it, but to optimize it we need to detect it, and I will show you briefly how we detect our molecules. We do it by resonant absorption. For this we have a laser, which is a titanium sapphire laser, that red light pumped by a green laser, and with this optica we make multiple beams of it, put it in optical fibers, and also reduce intensities and polarization control. And so if we then look in time, we see our absorption laser, we measure the intensity, and if there's an ablation, some time later, barium fluoride molecules fly through the absorption laser and will absorb some light. And this leads to some extinction, and we can detect our molecules. This is all very state selective, so we know exactly the internal behavior of the barium fluoride molecules. So with this source, we want to optimize our source, make as much as possible barium fluoride molecules. And now you go to Groningen and see what you can do with those molecules.
Hi, I'm Hanno. I'm also part of the NL-EDM collaboration. Here in Groningen, we also have a cryogenic source, like the one Maarten has in Amsterdam. Here we have the Stark decelerator behind it. So for a Stark decelerator, we need high voltages. And these are in these amplifiers. So we have 8 amplifier boxes, since we have